Hello, everyone. So we are moving on to something that's very similar to limits, is continuity. So start with this do now. It's based on what we did the other day. So I'm going to use this. This was our average rate of change formula. So we're going to do the limit as x approaches. Now I gave you c is 8. So first we write f of x. So the square root of x minus 4 plus 1. Now we're going to subtract f of c. So that's f of 8. If I plug 8 in, I get the square root of 4 plus 1, which is 3. So I'm subtracting 3 all over x minus 8. I'm going to simplify that to the limit as x approaches 8. The square root of x minus 4 minus 2 all over x minus 8. Now, if you try to plug 8 in, you end up getting 0 over 0. So that means we have to do something. Anytime you have a square root, we end up rationalizing. So I'm going to multiply the top and the bottom by the square root of x minus 4 minus 2. Square root of x minus 4 minus 2. So now the top, square root of x minus 4 minus the square root of x minus 4 is just x minus 4. Because we have x approaching 8, we don't have to worry about an absolute value. Negative 2 times negative 2 is plus 4. Did I do something wrong? Oh, wow. That's such a baby mistake. It's minus. Oh my god. It's already minus, so then I have to do a plus. We changed the sign. I can't believe I never make that mistake. Whew. Apparently my brain is gone today. All right, so it's minus 4 all over. Now just leave the bottom the same. Don't multiply that out, trust me. All right, so then what happens? This numerator is really x minus 8. So my x minus 8's cancel. So this cancels with this. Now be careful. A lot of kids will drop that numerator. This is now the limit as x approaches 8 of 1 over x minus 4 plus 2. So now that we don't get 0 over 0, we plug in and we get 1 over 4 as our final answer. All right, so write this down. Definition, continuity at a number. Continuity. A function f is continuous at a number c if the following 3 conditions are met. F of c is defined, so we have to have it in the domain. The limit exists, and the limit equals the function value. So for example, if you think about a polynomial, right? Polynomial, nice smooth curve. No matter where you pick, the domain exists. The limit exists, and the limit is always the function value, right? There's no holes. We don't have something like that. In this case, the limit exists, however, it does not equal the function value. We want the limit and the function value to be the same. Another way we say that is, can you draw it without picking up your pencil? Right? Not like drawing it like that. That's cheating. I'm talking, can you draw it without picking your pencil up and there's no gaps or anything weird happening in the graph? So keep in mind, the number is in the domain, the limit exists, and the limit equals the function value. All right, so determine whether f of x is continuous at 4. So think about what this graph is. So the answer is yes. Because x equals 4 is in the domain of f of x. The limit as x approaches 4 equals f of 4. So I talked about all three statements. It's in the domain, the limit exists, and it equals the function value, okay? You have to, yeah, and when it says determine, we're actually saying these words. We have to write sentences, get used to it in calculus. It's not crazy, we're not writing essays, but a couple sentences here and there are important. All right, try number 2 on your own. Determine whether g of x equals x plus 8 over 4 minus x squared is continuous at x equals negative 2. Is that continuous? It is not. And what is the reason? No, g is not continuous because, why? X equals negative 2 is not in the domain of g, right? The domain of that is all real numbers except 2 and negative 2. So that cannot be continuous because that point is not in the domain. All right, determine whether h is continuous at negative 3, 0, and 3. So pause the video and try this one. So let's see. H is continuous at which one? At x equals 0, since it is in the domain the limit as x approaches 0 of h of x is the square root of 2 over negative 9, and h of 0 equals square root of 2 over negative 9. It's another way of putting it. So the limit exists that equals the function value, and x equals 0 is in the domain. However, h is not continuous at x equals plus or minus 3 because they are not in the domain of h, right? There's vertical asymptotes at those points. 5. Oh. All right, determine whether the piecewise function is continuous at x equals 5. All right, so we know that it's in the domain, right? X is in the domain because of this. Now we have to check, does the limit exist? So what's the limit as x approaches 5? So the limit as x approaches 5 from the left of f of x, that's the top function, right? Now if we try to plug 5 into this, that doesn't work. So what do? We can cancel, right? We talked about this the other day. So if I cancel x plus 5, x minus 5 over x minus 5, cancels out, and then we plug 5 in, we get 10. So the limit from the left is 10. The limit from the right is also 10, right? Because if we plug in here, and so the limit is 10, so we know the limit exists. Does the limit equal the function value? That's a no. So no, because the limit as x approaches 5, f of x equals 10, which does not equal f of 5, because f of 5 is 25. 10 and 25 are different numbers. So this is an example where the limit exists, but it's not equal to the function value, right? So you have the whole, and then you have the random dot. We want, for it to be continuous, we want this to fill that hole in. All right. Let f be a function that is defined everywhere in an open interval containing c except possibly c. The number c is called a removable discontinuity of f if the function is discontinuous but the limit exists. So that's like that last problem we just talked about. The discontinuity is removed by defining or redefining the value f of f at c to be the limit. So in that last problem, we had the issue where the limit was 10, but the function value was 25. So we call that removable because we can just be like, I'm going to change my mind. I don't want that to be 25 anymore. I'm just going to make it 10. If we just choose 10 and make that change, now it's a continuous function. So removable discontinuity is when you have the whole and then you have a dot somewhere else. Because what we can do, it's removable if we take that away and then fill the hole in, we're good. All right, so for each of these values, these are x values, is the function continuous? And if it's not, is it a removable discontinuity? So pause the video and do these on your own. So number 5 is not continuous, and it's not removable. Because the limit from the left and the right are different, it's not removable. See, -1, that is continuous. Right, -1, we have a dot there, nice. 2, not continuous. And that is not removable. Again, we call that a jump, so it's not removable. And then 4, that is not continuous because there's a hole. But this is the example where it is removable because I can redefine my function and say, okay, instead of being at 5, I'm going to change that to a 2. So this is removable. Removable discontinuity. Okay. All right, define f of c so that the function is continuous. So we've talked about this one before. We've tried to find the limit, right? This has a discontinuity at 7 because if we plug in 7, we get 0 over 0. 7 is not in the domain, right? 7 is not in the domain. So we're going to define it that way. So we need to find the limit as x approaches 7 because we want the limit to be the same as the function value. So what did we do here? Well, it's a square root. Whenever we have a square root, we multiply by the reciprocal.